Hello, so I'm going to do something that I haven't done before. I'm going to solve three problems in one because they're relatively simple and they all talk about, um, they all build up to the same circuit eventually. But I took a shortcut here, if you would forgive me. I went ahead and highlighted all the given in terms of red. Now, to mention, we're given the circuit here and that it has a AC voltage source, AC input for this circuit. We're talking about AC circuits now. Um, and all the goals that we're trying to find are in blue. And I've already written down all the formulas that we'll need as well. Okay? So what only needs to be done is to solve, but take note, we're doing three problems. So bear with me. We'll get through this together. Okay? So this first problem it's an AC circuit. So this equation actually is a basic wave equation. How do I know that? Because it has a sine function in it. The 2 pi f is actually the what's called the angular frequency, known as angular velocity in other cases. But this number right here, if you notice, is already RV max. It's the amplitude of the wave. So if this were the 0 volts, then on top would be would be 200 volts, and the bottom here would be negative 200 volts. Okay, that wave. And we're asked to solve. We're given that the resistor in itself is pretty hefty. Well, not that much. 100 ohms. And actually there's not much of a use for this type of circuit, just a resistor and a input source. Not so much different from those in past chapters. But we're going to build all this up together to make an RLC circuit. So let's get into it. Okay, solution right here. Okay, so since I already know that the V max is 200 volts, the peak or the trough, then I just need to find the RMS, which is, that one's easy. That's just 200 volts divided by square root of 2. Now this should result in something that is smaller than 200, and sure enough, that gives us actually kind of the digits for square root of 2. And then from there, I'm going to use good old Ohm's law to solve for the RMS current. Now what I need to do for this formula is divide both sides by R, boom, to get I forgot to write that R somewhere. So this is 141 RMS voltage divided by 100 ohms. So that's pretty easy. Just move the decimal place to ends, and then in this set of units should end up being in terms of amperes. Okay? And there we go. Let's make this nice and clean. Those are our two answers for the RMS voltage and the RMS current flowing through this resistor right here. Okay, so not wasting any time, going on to the next problem. Now we've replaced the resistor with a capacitor. Now remember that capacitors also take a while to charge up and also a while to lose its charge. There's a time constant. Almost acts like it's resisting the current, because when it's fully charged to the volts here, it will actually block the current, and that's why we have the capacitive reactance. The capacitive reactance will actually be in terms of units of ohms, as you can see, because it's placed here in Ohm's law. Okay, so this is actually literally a plug and chug problem. We're giving that the capacitor is 8 microfarads. Remember that micro means 10 to the negative 6. We're actually given a different RMS voltage this time. This is 150, and a frequency of 60 hertz, something we didn't have before. So, but is everything we have, everything that we need, rather, to solve this problem. So for the capacitor reactance, it's literally plug and chug. Don't forget the micro. That's going to be important, but that's farads, not coulombs. Okay, now one interesting thing to note here is that since we're divided by -6, 1 over -6 should actually result in a relatively big number. Okay, so let's find out what this is. And the units I should end up with, oops, need a pen, are in ohms, and that actually result into 332 ohms. Put that in red. Okay, don't ask me how hertz and farads become ohms, but I'm pretty sure they do. I think it's because you can definitely, I'm sure that you can show that, but I'm not going to show that right here now. Just take that it is equal to ohms for now. So here I'm once again looking for the RMS current, so I just need to find both sides of Ohm's law for a capacitive AC circuit, and then I will get the formula that I need to find the RMS current flowing through this purely capacitive AC circuit. We're given the RMS voltage, it's a little bit bigger than the one we had earlier, and divide by the 332 ohms, and that should give us units once again in terms of amperes. That results, since what we have, take a look at this. We have 150 and we have 300, about-ish, so it should result in something that's like close to half, but this is actually bigger than 300, so it should be something that's less than 0.5. And sure enough, our answer for the current is less than a half of an ampere. Okay, and that solves this problem because we said we were looking for the RMS current and the capacitive reactance, which is measured in terms of ohms. But what if we can change that into a inductor, which is actually the next example right here. Okay, this actually has the same RMS voltage, the same frequency, because remember it's a waveform, so frequency is just one of the properties of a wave, whether it's transverse or longitudinal. But now we're given inductance. Remember milli, don't forget your conversions, it's 10 to the -3. And very similar to the one problem before, find now this time the inductive reactance, which has a different formula, and RMS current as well. Now we expect that the RMS currents for each one of these should be different, especially if they have different values and they're talking about different things. Okay, so let's take a look at this. I'm just going to plug in my values that I've given for inductive reactance. 2 pi, still 60 hertz. Now once again, not quite sure how hertz and henries times henries becomes ohms, but we'll save that for another time. Don't forget the conversion units. And all I know, that should equal to something ohms. And I guess not surprising enough, an inductor doesn't really have that much resistance. It also depends on the value that we're using here too. So it's about 9 ohms, 9.5, almost close. And once again, to solve for the RMS current going through the inductor, it's L, not C. but now I'm dividing this by a much smaller number. So I expect this number to be relatively big. Okay, so trying that out, I get, wow, look at that. Oh my gosh. 15.9 amps. That is a lot of juice flowing through. That is definitely big current. Wait, current. Okay, make sure your units are right. So, but take note that the current is also in a waveform as well. This is just the RMS. Oh wow, this is just the RMS. This is not even the maximum value. So it kind of boosted a little bit after a while of resisting it. Okay, so what happens if you add inductor and a capacitor and a resistor all together in series, not parallel, because that would kind of defeat the purpose. That's probably for a different type of circuit. But look forward to the next example where we combine a resistor, an inductor, and a capacitor all in one circuit. Okay? Hope you're able to, you can feel free to pause or to rewind as you wish this video. Hope you all enjoyed. Ciao.